You are in for a treat today. I'm going to show you how to balance any rotating equipment with an earbud speaker, a magnet, and a scrap piece of steel. Stick around. And right off the hop here, I want to thank Jacob Barton, commenter on the default grinder teardown. In response to my kind of query about the sheepskin Buna N condom on the back of the rotor, he had mentioned that likely it's to decrease rigidity to eliminate nodes, vibration nodes, in the motor itself. And that set me to thinking. One of the things that you notice first when you first start using a tool, especially a cheaper tool, is that it shakes in your hand and it doesn't feel very nice. But I'm not the guy that does shill paid reviews and says, this tool feels so good in the hand. I need numbers. I need to quantify how it feels in your hand. So I set to thinking in my head, which is where I do most of my thinking. How are we going to check the vibration in these tools without $50,000 worth of industrial vibe tools? So I thought the data logging capability of the Rigol scope would come in handy, but not all of us have a $400 scope, and frankly they have yet to pay me my royalty check, dirty bastards. So I figured we cut them out of the equation. We do it even simpler. So this is the surface mount inductor that I used. There's a little HPHT on there for checking the RPM of the drill motor after my Blue Point Phototac packed it in. And I thought to myself, well, this is great, but not everybody has one of these. Not everybody's a dork like me, so where are they going to get something like that? And then I thought to myself, well, pretty much everybody has an earbud, and who the hell doesn't have neodymium magnets? Who the hell doesn't have old chunks of scrap laying around? And obviously they got a confuser. So how are they watching this video? So here's the setup. We've opened up Audacity in the confuser and we've set up our earbud into the microphone port. Now watch what happens when we ping this member. So what we can see there is the natural frequency of this system. And the natural frequency is the frequency at which this thing wants to vibrate. Now there's all those hoary old stories about soldiers marching in lockstep and destroying bridges, and there's also that bridge in the windstorm, I think in Tacoma, that fell down. Now luckily for us, engineers are smarter than that nowadays, and they build in dampening so that doesn't happen. So this video is not going to help any terrorists destroy any buildings or anything like that. But what happens is if we can measure the natural frequency and then get something else to run at that same frequency, the thing will start to vibrate like crazy, unless of course there's some dampening. Okay, so now I'm going to take a screenshot and check the natural frequency here. So we're just taking this section here, this natural frequency, and we're going to do a low pass filter on it. Now we can expect that the low pass filter allows low frequencies. We're not going to go anything above 30 Hertz. So now we'll do a high pass filter, and we don't want anything below 4 Hertz looks good. Okay. Now we're going to analyze, and we're going to do a FFT, a fast Fourier transform. It doesn't tell you that it's doing that, but this is what it's doing. And we got it set up for spectrum with the Hamming window and that many somethings, and it's log frequency. So now, if we look at this guy here, 5 Hertz, 10 Hertz, 17 Hertz, 20 Hertz. This should actually be more like 15 Hertz. But what we're seeing here is the natural frequency and the nodes of this system. This guy's easy. It's at 11 Hertz. We'll say that's at 10 Hertz. Times 60 is 600 RPM. So if we turn the drill at 600 RPM, we're going to get a hell of a speed wobble on that cantilevered piece of steel. Don't believe me? I'll prove it. Okay, we're taking a screenshot and we're just going to speed this up. And you will see we will start to get an oscillation, even though this thing is pretty balanced. There we go. So that is the natural frequency of this system. Whatever RPM that's at, change that to hertz by dividing by 60, and we get the natural frequency. Then actually, if we find out what that frequency is, and we add it to this base frequency, we'll find a node, and that should make it vibrate as well. Although, according to the FFT transform, that graph I showed you, it's not going to have the same amplitude, so it won't shake as much. There we go. There's another node. You can see it's shaking a little bit. And all I'm doing to control the speed here is I got the trigger electricity down, and we're just running the trusty old variac. Okay, so as you can see here, I made a little cognitive error because we're starting to pick up the actual sound of the drill. We don't want the sound of the drill. We want the sound of that magnet interfering with the magnetic field in the earbud and making that little waveform. We don't want the sound. So the way we're going to get rid of that is by putting a piece of tape over the air holes. And in this run, I'm also going to turn on the laser, the UV laser, and the glow-in-the-dark target, because a lot of guys are super visual, and it helps to explain things if you can just paint them a picture. So this is that. I'll channel Picasso here just for you. And remember, this is with a balanced tool. This is, although it is a default, it's not a bad tool, and it does have a chintzy plastic chuck. It's still what I would consider a good quality tool. So it's pretty well balanced, and you can see it's still getting a nice speed wobble in there. So what happens if we purposely unbalance it, or we put a piece of equipment on there that's completely unbalanced? What's that going to look like? Of course, having this hooked up to the computer and Audacity is fun, but it's not really necessary. All you need is something that will mark the oscillation. And what we're using here is a laser and a UV target. And the more that moves up and down, the more off balance it is, regardless of what speed it's turning. So you can turn it at any speed, and if it's out of balance, it'll shake a lot more than, obviously, if it's in balance. So you can go ahead and use that knowledge to balance your equipment. Now, if you look at the amplitude of this sine wave, you'll be able to tell how much of a speed wobble you have, and then you can go ahead and put counterweights on there to correct that speed wobble. So we've got this thing way off balance, and we're going to bring it up to speed slowly. Now we've got this completely out of whack. Now we can go ahead and bring this up to speed and capture the data with Audacity. Then we can treat that data to see where the spikes are, and that will tell us the natural resonant frequencies that this system will shake itself apart at. That way we can avoid those or repair them. Well, we're getting a little dampening happening there because I just taped it on with electrician's tape. It's not a rigid. And you can see that smooth right out, even though it's way off balance. Now let's go back and hit the natural frequency of this system. Just 600 RPM. 10 hertz. Oh, look at that. Shaking itself all to hell. I love this because it's the minimum viable method for balancing any rotating equipment. High speed, low speed, doesn't matter. Super simple. And if you have a big motor, you just get yourself a beefier cantilever, bolt it down, no big deal. So now we have a method for quantifying the hand feel quality of tools by how much it weeble wobbles. And actually in future, if you wanted to log this without any electronics, the very simple way to do it is with pencil and paper. Thanks a lot for watching. Keep your stick on the ice.
All right, lift off and the clock has started. Yes, sir, reading you loud and clear.